Last time we have seen to obtain the solution of a non-homogeneous differential equation if the q of x is equal to e to the power ax, and we have seen the two theorems. The first theorem is if f of a is not equal to 0, then 1 upon f of t operate on e to the power ax is equal to e to the power ax upon f of a. This is the first theorem. And in the second theorem, if f of a is 0, then what we have to do? Now suppose this f of a is 0, this means that d minus a is a factor of f of d. Suppose this factor repeated r times. Suppose this factor repeated r times. Means if f of d is equal to d minus a to the power r into phi of d, where phi of a is not equal to 0. Then we have seen the second theorem. In the second theorem, we have seen that if f of d is equal to d minus a to the power r into phi of d, where phi of a is not equal to 0, then 1 upon f of d operate on e to the power ax is equal to 1 upon d minus a to the power r into phi of d operate on e to the power ax, and this is equal to x to the power r e to the power ax upon r factorial into phi of a. We have seen these two theorems in the previous lecture. Now we want to see the example based on this. Consider this first example. Solve the equation d cube minus d square plus 8d minus 4 of y is equal to e to the power 2x plus 2e to the power x plus 3 e to the power minus x. We want to obtain the general solution of this non-homogeneous differential equation. And we know that the general solution contains the two parts. The first is the complementary function, and second, the particular integral or particular solution. Now to find the complementary function, for this purpose, we find the general solution of associated differential equation, and the general solution of associated differential equation of given non-homogeneous differential equation is called the complementary function of given non-homogeneous differential equation. First, we find the solution of this associated homogeneous differential equation. In the previous topic, we have seen how to obtain the general solution of homogeneous differential equation. Now, we consider this given differential equation. From this, we write the auxiliary equation. This is the associated homogeneous differential equation. We consider right hand side dash to be 0. From this, we take the auxiliary equation. This is the auxiliary equation. Now factorize this. We know that how to find the factors of the left hand side of this equation of the auxiliary equation. The factors are m minus 1 and m minus 2 bracket square is equal to 0. Means the values of 1 is the values of m are 1, 2, 2. These are the roots of the auxiliary equations. One root is real and distinct, and two roots are real and repeated. According to that, we write the general solution of this associated homogeneous differential equation, and we call this general solution as to be the complementary function of this non-homogeneous differential equation, and we denote it by yc. Therefore, yc is equal to c1 e to the power 1 into x, means e to the power x, plus in the bracket c2 plus c3 x bracket complete e to the power 2x. This is our complementary function. Yc is c1 e to the power x plus c2 plus c3x into e to the power 2x. This is the easy part. We have seen this already in the previous topic. Now we want to find the particular integral or particular solution of this non-homogeneous linear differential equation. Now for that purpose, we denote it by yp. Yp is equal to 1 upon f of t operate on q of x. Here q of x is e to the power 2x plus 2 e to the power x plus 3 e to the power minus x. Therefore, we obtain particular integral yp is equal to 1 upon f of d is d cube minus d square plus 8d minus 4. Operate this on e to the power 2x plus 2 e to the power x plus 3 e to the power minus x, and we write the factors of this f of t. Then yp is equal to 1 upon, we write the factors from this 1 upon d minus 1 into d minus 2 bracket square, operate on this e to the power 2x plus 2 e to the power x plus 3 e to the power minus x. We obtain this step. Particular integral is this. Now we operate this operator one by one on this. We take first 1 upon d minus 1 into d minus 2 square, operate on e to the power 2x plus 1 upon d minus 1 into d minus 2 square, operate on 2 e to the power x plus 1 upon d minus 1 d minus 2 square, operate on 3 e to the power minus x. Or we may take this constant to be outside of this operator. We obtain this step. Now we want to operate 1 upon d minus 1 d minus 2 bracket square on e to the power 2x. Now here in this denominator, if we substitute d by 2, then what happens? This term becomes 0. If we substitute d by 2, then this term becomes 0. Therefore, by the second theorem, we call this term as to be d minus a to the power r, right? By second term, we call this as to be d minus a to the power r. Here a is to be 2 and r is 2. Here if we substitute d by 2, then 2 minus 1 is 1, means it is non-zero. This is phi of d. Means we call this as to be d minus a to the power r into phi of d. Try to understand this properly. Here a is 2, r is 2, and phi of d is d minus 1. Means in the result we have seen, if we operate 1 upon d minus a to the power r into phi of t on e to the power ax is equal to x to the power r e to the power ax upon r factorial into phi of a. In that result, if we substitute the quantity as to be a is 2, r is 2, then what happens? And phi of d is d minus 1. Then what happens? This is equal to x to the power r, means x square, e to the power ax, means e to the power 2x, means the numerator is x square e to the power 2x divided by r factorial, means 2 factorial, and into phi of a, means into 2 minus 1. Means our first term is numerator x square e to the power 2x and denominator is 2 factorial into bracket 2 minus 1. Are you understand this first? The same way for the second term, if we see for the second term here a is 1, if we substitute d by 1, then this bracket, this becomes 0 and this is non-zero. Therefore, we call this as to be phi of d. For the second term, phi of d is d minus 2 to the power 2. Means in the bracket d minus 2 bracket complete its square. This is our phi of d. And here r is 1. This is the first factor, d minus a to the power r. A is 1, r is 1. Here, see here phi of d is this. Here phi of d is this. And here from this we choose r. Here from this we choose r. Here r is 1. A is 1. And phi of d is d minus 2 whole square. Correct? Therefore, again using that result 2 as it is, x to the power 1, e to the power x upon 1 factorial into bracket 1 minus 2 bracket complete its square. This is the second term. Now for the third term, here a is minus 1. If we substitute d by minus 1, then the first bracket is non-zero and also the second bracket is non-zero. Therefore, we can use the theorem 1. For this, we use the theorem 1 directly. We substitute d by minus 1. Means we obtain 3 e to the power minus x divided by, in the first bracket, minus 1 and in the second bracket, minus 1 minus 2 bracket square. In this way, we write the terms to be here. This is the steps I have explained you completely. X square e to the power 2x upon 2 factorial into 2 minus 1. For the second 2x e to the power x, 1 minus 2 bracket square into 1 factorial plus 3 e to the power minus x minus 1 and in the second bracket minus 1 minus 2 bracket square. Only we want to simplify this. 2 factorial is 2 into 1 is 2. 2 minus 1 is 1. Means here in the first term the denominator is 2. For the second, 1 minus 2 its square is minus 1 square is plus 1. 1 factorial is 1. 1 into 1 is 1. Therefore, there is no denominator in the second term. We get 2x e to the power x. Now, for the third term, denominator is minus 1 minus 2 bracket square minus 3 square is 9. And this minus 2 minus 18. 3 divided by minus 18. 3 gets cancelled, means we get minus 1 upon 6. The third term is e to the power minus x upon minus 6. After simplification, we get this term. This is our yp. And we know that yc and yp, then we write the general solution. Therefore, the general solution is y is equal to yc plus yp. And this is equal to c1 e to the power x plus in the bracket C2 plus C3x bracket complete e to the power 2x plus x square into e to the power 2x upon 2 plus 2x e to the power x minus 1 upon 6 e to the power minus x. This is the general solution of the given differential equation. Now we see the another example. Solve this equation. Now we see the solution of this again by the same method. The given differential equation is this. Associated differential equation is in the bracket d to the power 4 minus d cube plus d minus 1 bracket complete of y equal to 0. From that we write the auxiliary equation is m to the power 4 minus m cube plus m minus 1 is equal to 0. Now we want to factorize this. After factorizing, we get the factor as to be m minus 1, m plus 1, m square minus m plus 1 is equal to 0. The last factor is the quadratic irreducible factors, and we know that how to factorize this. We know the formula for that: minus b plus or minus under root of b square minus 4ac upon 2a. You may write in that way, or you may rearrange this term as to be the last term only I have explained you. In the square bracket, in the open bracket, m minus 1 half bracket square. Means we obtain the first two terms, m square minus m. The additional term is 1 upon 4 plus 1 upon 4. If we subtract from the second one, minus 1 upon 4 means this is 3 upon 4. Means the first bracket is m minus 1 half bracket square plus 3 upon 4. And we factorize this as to be m minus 1 half plus root 3 upon 2i, and the second bracket m minus 1 half minus root 3 upon 2i. You may factorize by any method, then we obtain the values of m has to be 1 minus 1 plus 1 half plus or minus root 3 upon 2i. These are the roots of the auxiliary equation. Therefore, the general solution of associated differential equation is, or we call this general solution as to be complementary function of given non-homogeneous differential equation, and we denote it by YC. Therefore, here YC is equal to C1 e to the power x plus C2 e to the power minus x plus e to the power 1 half into x into bracket C3 cos root 3 upon 2x plus C4 sin root 3 upon 2x. We have seen if the roots are real and distinct, how to write the terms. If the roots are complex and non-repeated, then how to write the terms in the solution. We have seen this in the first topic. Using that result, we are able to write this complementary function. Now we are interested to find the particular integral yp. Yp is equal to 1 upon f of t operate on q of x. Here q of x is e to the power x minus 2, and we operate 1 upon d minus 1, d plus 1, d square minus d plus 1 on e to the power x minus 2. Then we operate this factor 1 by 1. First, we operate this factor e to the power x, and then we operate this factor. We write this minus 2 as to be minus 2 into e to the power 0x. E to the power 0x is 1. And then we take minus 2 constant outside of this operator, and we operate this on e to the power 0x. Now, see here for the first term, what happens for the first term here? If we here a is 1, if we substitute d by 1, this becomes 0, and this is non-zero if we substitute d by 1. Therefore, whole this we call as to be phi of d. Means in this case, our phi of d is what? D plus 1 into d square minus d plus 1. And from this first factor, d minus a to the power r, here r is 1. Means for the first r is 1, a is 1, and phi of d and phi of d is to be d plus 1 into d square minus d plus 1. If we substitute this in our second result, we have seen, we get x to the power 1 means x e to the power x divided by 1 factorial into bracket 1 plus 1 in the another bracket 1 square minus 1 plus 1. Now for the second term, if we substitute d by 0, then this denominator is non-zero. Therefore, by theorem 1, we directly substitute d by 0. We get this after substituting. 1 factorial is to be 1. And after simplification, we get yp is equal to x e to the power x upon 2 plus 2. And then we write the general solution. Yc plus yp. This is the solution of given differential equation. We have seen that this is the second example. Now we see the third example. Solve the equation d cube minus 2d square minus 5d plus 6 into y, or operate on y, is equal to e to the power 4x. If we want to find the solution, this is the given differential equation. From this, we consider the associated homogeneous differential equation. Then we write the auxiliary equation. We factorize this. We obtain the roots are real and distinct, and this is the complementary function. We have seen all these things in the previous topic. This is very easy up to this. Yc is equal to c1 e to the power x plus c2 e to the power minus 2x plus c3 e to the power 3x. Now we want to find the particular integral. Yp is equal to 1 upon f of d, operate on q of x. Means here yp is equal to 1 upon d minus 1, d plus 2, d minus 3, operate on e to the power 4x. Now here directly, if we substitute here a is 4, compare this with 1 upon f of d, operate on e to the power ax. Here a is 4. If we substitute d by 4, the denominator is non-zero. Therefore, we directly substitute here d by 4 by using our theorem 1. And we get this. After simplification, this is our yp. And therefore, write the general solution as to be yc plus yp. And this is equal to c1 a to the power x plus c2 e to the power minus 2x plus c3 e to the power 3x plus e to the power 4x upon 18. Now we see one more example. Consider this. Obtain the general solution of d square minus 6d plus 9 of y is equal to e to the power x. Now the given differential equation is this. From this associated differential equation is this. Then we take the auxiliary equation as to be m square minus 6m plus 9 is equal to 0. Then its roots are 3, 3. Factorize this. This is m minus 3 bracket square is equal to 0. The roots are real and repeated. Therefore, complementary function yc is equal to in the bracket c1 plus c2x bracket complete e to the power 3x. Now to find the particular integral, we take yp is equal to 1 upon f of d, operate on q of x. Here yp is equal to 1 upon f of d, d minus 3 bracket square, operate on e to the power x. Again here a is 1. If we substitute d by 1 directly, then denominator is non-zero. That's why we substitute here d by 1 directly, and we get this. Yp is e to the power x upon 4. And from this, we write the general solution. You have seen the 4 examples on this type. If q of x is e to the power ax, then when we find particular integral, we have to use the two theorems. We have seen these two theorems. With the help of these two theorems, we are able to find the particular integral very easily as compared to the general method. This is the particular type of some short method to find the particular integral. Now take these examples for practice. Obtain the general solution of following differential equations. Or in the examination, they say that only solve, meaning is the same. The first is y double dash plus 4y dash plus 3y equal to 15 e to the power 2x plus e to the power minus x. Second example, y double dash minus 3y dash minus 4y is equal to 30 e to the power x dash indicates the derivative with respect to x as our usual meaning. Now the third in the bracket d square minus 3d plus 2 bracket complete of y is equal to e to the power 2x plus 5. These are the examples for practice. You saw these examples. Now we stop our today's lecture.